Welcome to Dreamtime Science, where curiosity meets tranquility and knowledge flows like a gentle stream. Here we explore the wonders of our universe at a pace that soothes the mind. You know what's fascinating? I've been thinking about how something as tiny as an electron can set off a chain reaction that lights up entire cities. There's something remarkable about how these invisible particles dance through wires and transform into the power that hums quietly in our homes. Tonight, I'd love to share that journey, from the spark of an electron to the vast humming network of power grids that feels like a gentle, unseen magic all around us. Your gentle engagement through likes and subscriptions illuminates this quiet corner of knowledge. Let me know in the comments what scientific mysteries you'd love to explore together. Let's prepare for tonight's journey. Find your most comfortable position, let tension float away from your body, and take 3 slow, peaceful breaths. Close your eyes and let your breath settle as you drift toward the edge of sleep. In the gentle hush, imagine a world before the hum of wires, before the flicker of light bulbs, before even the word electricity had entered any tongue. The darkness was thick and deep, broken only by the starlight above and the occasional terrifying miracle of lightning clawing the sky. In those moments, the universe itself seemed to awaken and roar, the air splitting with a crack that made even the bravest hearts falter. Yet in that ancient awe our story begins, for lightning is but the wildest cousin of the same force that now powers our cities, our homes, our tiniest devices. Electricity. The word itself dances on the tongue, sharp, bright, almost alive. It is the invisible river that powers reality's machinery, the restless motion of particles too small to see, yet whose effects shape the very world. To understand this spark, we must first descend, shrink ourselves in imagination to a scale beneath the gaze of any microscope. Here, in the realm of the atom, the world is built not of solid things, but of whirling clouds and darting specks. At the heart of every atom, a dense core of protons and neutrons clings together, heavy with mass and charge. Spinning around them, as if in a cosmic ballet, are the electrons, minuscule, negative, elusive. These electrons are the true bearers of electric charge. Each one carries a quantum of negativity, a tiny but fundamental property of matter, as if the universe itself decreed that some particles would forever repel and attract according to rules older than the stars. It is the movement of these electrons, their restless migration from atom to atom and through the tangled lattice of matter, that births what we call electric current. In a chunk of copper wire, for instance, most electrons are tightly bound to their parent atoms, but some, the so-called conduction electrons, are freer, more adventurous. They slip between atoms, forming a sea of charge that can be nudged into motion. When you close a circuit, switching on a lamp or pressing the power button on a computer, you are opening a path, a gentle invitation for electrons to flow. They surge forward, not at the speed of sound or even sight, but at a stately drift, like a slow tide moving through the metal. Yet the effect is practically instantaneous, for in this grand relay, the push at one end sends a ripple through the entire length of the wire. Electricity is not just the domain of wires and gadgets. It courses through the living as well, for our nerves speak to our muscles with tiny bursts of electrical signals. Every thought, every heartbeat, every flicker of memory is underwritten by the subtle dance of ions, charged particles, across membranes, leaping from neuron to neuron in patterns more intricate than any circuit board. The language of life itself is, in part, electrical. But long before electrons were weighed or named, humans felt the shiver of electricity in the world around them. There are stories from ancient Greece of amber rubbed with fur and then used to attract wisps of straw. The word electricity itself comes from electron, the Greek word for amber, that fossilized sap which, when stroked, would reveal its mysterious power. To the observers, it seemed as if some spirit had possessed the amber, making it reach and pull at distant things. This was static electricity, charges building up on the surface, longing to leap across the air. Centuries would pass before anyone glimpsed the deeper unity behind such phenomena. In the 18th century, the air crackled with curiosity. The salons and laboratories of Europe buzzed with tales of strange machines, glass globes spun on axles, rods that could summon sparks, Leyden jars that could trap lightning itself. People lined up to receive shocks, to watch the blue tendrils leap across gaps, to feel the tickle and tingle of unseen forces. Electricity was at once a parlour trick, a scientific marvel, and an object of deep speculation. It was into this world that Benjamin Franklin strode, spectacles perched and mind alight with wonder. Popular legend paints him in a storm, string in hand, flying a kite into the tempest to summon down the lightning, a picture so vivid, so mythic, that it has burned itself into the collective imagination. Yet the truth, as is often the case, is subtler. Franklin did fly his kite, but the experiment was a careful test, not a reckless bid to grasp the fire of the gods. He sought to show that lightning and the gentle sparks from a rubbed rod were, in essence, the same. By drawing a spark from a wet string, he proved the storm's power was kin to the electricity of the laboratory. But Franklin did not discover electricity, nor did he invent it, for it was never hidden. It was always there, woven into the fabric of matter and sky. What Franklin and his contemporaries did was more profound. They began to reveal electricity's unity, its rules, its potential for harnessing. They moved it from the realm of magic and spectacle to that of science and eventually technology. By the dawn of the 19th century, the torch was taken up by others. Alessandro Volta discovered that certain metals, bathed in acid, would set electrons loose in a steady current. This was the birth of the battery, the voltaic pile, and with it came the promise of electricity unbound from weather and whim. Michael Faraday followed, coaxing electricity from motion, spinning copper in the embrace of magnets, unveiling the secret of electromagnetic induction. With these discoveries, the age of electricity began to dawn. Yet in the popular imagination, electricity has always retained a hint of magic. It flashes and crackles, leaps and shocks, a force that can both give life and snatch it away. Nowhere is this duality more evident than in the stories we tell, stories of gods, heroes, and mortals who command the lightning. Consider Thor, the Norse god transposed into the vivid panels of comic books and cinema. His hammer calls the storm, his arms command bolts that shatter mountains. In these tales, electricity is raw power, elemental and absolute, a weapon and a blessing. Or take Storm, the regal mutant of the X-Men, whose eyes turn white as she summons thunderheads, bending the weather to her will. Even the very name Storm conjures images of charged air, of the world caught in the breathless pause before the strike. These stories are more than mere fantasy. They are echoes of our fascination with electricity's mysteries. They express the longing to control what once terrified us, to wield the forces that crackle through the world. The sight of a superhero flinging lightning is thrilling precisely because it feels both wonderful and forbidden, a reminder of the fire Prometheus stole, now shaped to the will of humankind. Yet, for all their spectacle, these portrayals often bend the facts of physics. Lightning is not a thing to be plucked from the sky and hurled at will. It is a discharge, a sudden rebalancing of charge between cloud and ground, the air itself torn into a conductive path by the immense voltage built up in the storm. The energy in a typical lightning bolt is staggering, enough to light 100 homes for a few moments, compressed into a heartbeat. To command such energies, as mythic heroes do, would require not just courage, but an understanding and control far beyond what even our greatest scientists have achieved. Electricity remains a trickster in our stories, a force that can heal or harm, create or destroy. Frankenstein's monster, stitched together from the dead, is jolted to life by a surge of current, a poetic license that reflects the deep connection between electricity and the spark of life. In reality, the body's impulses are far subtler, the voltages measured in millivolts, the currents a whisper compared to the roaring shout of lightning. Yet the metaphor persists, for electricity seems always on the threshold between the living and the inanimate, a bridge between worlds. Beyond the pages of fiction and the reverberations of myth, electricity has become the lifeblood of civilization. The simple act of flipping a switch, so casual, so thoughtless, unleashes a cascade of events, a ballet of electrons that begins far away. Follow the wire back, and you may find yourself at the foot of a humming transformer, its coils thrumming with potential. Trace further, and you reach the power plant, where turbines spin, driven by falling water, burning coal, splitting atoms, or the push of the wind. Here, in these engines of modernity, the laws unveiled by Faraday and Volta are put to work on a vast scale, turning motion into current, current into light and warmth. The journey of electricity from atom to grid is a marvel of engineering and vision. Into the wires go the electrons, pushed by the force we call voltage, their path resisted by the obstacles of the material, what we call resistance. Ohm's law, as simple in form as it is profound in implication, links voltage, current, and resistance in an elegant trinity, V, X, I, R. Through this relationship, the invisible is made calculable, predictable, harnessable. Yet for all our mastery, electricity never truly stands still. Even in the quietest moment, currents flow inside the earth, in our bodies, in the restless dance of the aurora above the poles. The northern lights themselves are born of solar winds, charged particles from the sun, colliding with our planet's magnetic embrace, painting the sky in curtains and arcs of shimmering light. Nature's own electric show, unbidden, unstoppable. So, as you drift on the edge of sleep, know that the spark which starts the fire is both ancient and ever new. It is the same spark that once leapt from amber to straw, that surged through Franklin's kite string, that now hums in every wall and pulses through every device. It links the mythic to the scientific, the imagined to the real, the power of gods to the curiosity of mortals. Somewhere out there, the grid stretches on, wires spanning continents, substations pulsing, transformers humming their quiet song. The electrons do not care for our stories, yet they shape them all the same, running from the heart of the atom to the heart of our cities. Beneath this web, the world glows with potential, each light a testament to the restless, invisible charge that has always been there, waiting to be understood, harnessed, and perhaps wondered at anew. The spark is only the beginning. There are deeper mysteries ahead, currents beneath the surface, stories yet untold. There is a hush in the world at midnight, a silence that belies the ceaseless flow of energy beneath our feet and above our heads. While cities sleep and the countryside slumbers, the grid, the vast pulsing network of wires, transformers, and substations, whispers its ancient song, threading electrons from distant generators to the glowing lamp at your bedside. This web, this tapestry of lightning, is both marvelously robust and achingly fragile. Its workings are a testament to human ingenuity and a living reminder of the mysteries we have yet to untangle. Electricity, for all its familiarity, remains a subtle and elusive companion. We flick a switch and the room brightens. We plug in a device, and it hums to life. Yet behind this everyday magic lies a choreography of unimaginable complexity, a swirling dance of particles and potentials carried on copper veins stretched across continents. To truly understand the grid is to stand in awe of a force that is at once invisible and inescapable, domesticated and wild, mastered in part but never fully tamed. Let us begin with the journey of a single electron, born in the heart of a turbine, perhaps spun by the rush of water at a dam or the roar of gas in a power plant. This electron joins trillions of its siblings, each nudged along by the invisible hand of voltage. They march not in a steady stream, but in a trembling oscillation, back and forth, 60 times a second, at least in much of the world. This is alternating current, or AC, a phenomenon that seems simple but is in fact a triumph of both theoretical insight and practical engineering. The adoption of AC over direct current, DC, was not foreordained. In the twilight of the 19th century, the world teetered on the edge of a great electrical schism. On one side stood Thomas Edison, champion of DC, whose early power plants could light neighborhoods, but not much more. On the other was Nikola Tesla, a man born to dreams and thunder, who imagined a world linked by waves of oscillating current. Tesla saw that AC could be transformed, its voltage raised or lowered with mysterious ease by the humble transformer. This allowed power to be sent vast distances, leaping from generator to substation to household with minimal loss. Tesla's vision prevailed, and the modern grid was born, a monument to the strange and subtle properties of alternating current. Yet, with victory came complexity. AC's oscillations are both a blessing and a curse. They allow for efficient transmission, but they bring with them a need for constant balance between supply and demand, between phase and frequency, between the physics of electrons and the expectations of human society. Every moment, the grid is a tightrope walker, balancing the needs of millions against the relentless laws of physics. Demand rises and falls with the sun, with the weather, with the rhythms of life. If too much power is produced, the frequency of the grid creeps upward. If too little, it slips downward. Deviations, even tiny ones, can cascade into blackouts or equipment failures. The operators, perched in control rooms glowing with the light of 1,000 screens, are the conductors of this grand symphony, adjusting flows on the fly, dispatching reserves, rerouting currents, all to maintain a delicate equilibrium. Yet, for all its grandeur, the grid is haunted by ghosts of inefficiency. As electrons race through copper wires, some of their energy is shed as heat, lost to resistance. This loss is small for short distances, but over the hundreds or thousands of kilometers that power must sometimes travel, it becomes formidable. Here, the very nature of materials asserts itself. Copper and aluminum, for all their conductivity, are not perfect. They resist, they warm, they dissipate the precious energy we so carefully generate. This brings us to one of the strangest and most beautiful discoveries of the 20th century, superconductivity. Imagine a material through which electricity flows without resistance, where an electron can traverse a wire indefinitely, never slowed, never losing energy to the hungry embrace of heat. In 1911, Dutch physicist Heike Kamerlingh-Onnes, working in the chill of liquid helium, found that mercury, cooled to just a few degrees above absolute zero, lost all electrical resistance. The current, once started, would flow forever, undiminished. This was not just an incremental improvement, it was a revolution, a glimpse of a world where energy could be transported without waste. But nature, as ever, is not so easily conquered. Superconductivity, for all its promise, comes at a price. The temperatures required are unimaginably low, colder than the deepest reaches of the cosmos. Only with the advent of so-called high-temperature superconductors in the 1980s did practical applications begin to flicker on the horizon. Even these materials, with names as mysterious as their properties, yttrium, barium, copper oxide, for instance, require chilling with liquid nitrogen far below the comfort of everyday life. Still, the dream persists. Superconducting cables have been tested in cities like Essen and New York, carrying vast currents with scarcely a whisper of loss. In laboratories, magnetically levitated trains glide above superconducting tracks, and coils of wire trap magnetic fields in invisible cages. The puzzle is not yet solved. The physics of high-temperature superconductivity remains a labyrinth, its secrets guarded by the intricate dance of electrons paired in quantum embrace. Perhaps one day we will unravel the thread and reshape the grid in the image of this paradoxical perfection. Meanwhile, the limitations of our current grid remain. Chief among them is the challenge of storage. Electricity is a restless spirit, unwilling to be bottled or hoarded. When it is generated, it must be used almost immediately, or else it dissipates. For much of history, this was not a fatal flaw. Power plants could be throttled up or down as needed, and the grid's vast expanse allowed surpluses in one place to offset deficits in another. Yet, as our appetite for renewable energy grows, the need for storage becomes ever more urgent. The sun does not shine at night, the wind does not always blow. Solar panels and wind turbines generate power when nature allows, not when we demand it. The grid, so long accustomed to the steady heartbeat of fossil-fueled generators, now faces a future where supply is as variable as the weather. To bridge this gap, engineers have devised ingenious solutions. The most venerable is the pumped storage hydroelectric plant. When excess power floods the grid, electric pumps lift water to a reservoir perched high above the land. When demand surges, the water is released, plunging down through turbines to generate electricity anew. It is a simple idea, elegant and effective, but limited by geography and scale. In recent years, the rise of lithium-ion batteries has opened new vistas. These compact marvels, cousins to the cells that power your phone or laptop, can store energy for hours or even days, smoothing the peaks and valleys of renewable generation. Vast battery farms now stand sentinel at the edges of the grid, their containers humming quietly, poised to discharge or absorb power in the blink of an eye. Yet batteries are not panaceas. They age, they degrade, and their manufacture demands rare and precious materials. Other methods, still more exotic, are being explored. Compressed air, stored in underground caverns, can be released to spin turbines. Flywheels, spinning at dizzying speeds, store kinetic energy to be tapped when needed. Hydrogen, split from water by excess electricity, can be burned or fed into fuel cells to regenerate power. Each technique has its virtues and its flaws, its champions and its skeptics. The quest for the perfect storage medium is, in many ways, the modern alchemy, a search for a vessel that can safely hold the lightning we have learned to summon. All these innovations, all these struggles, occur within the latticework of the grid, a structure at once material and conceptual. Its physical manifestation is easy to see, the pylons marching across fields, the substations humming behind chain-link fences, the tangled skein of wires overhead. But its true nature is more elusive, a web of relationships and flows, of contracts and contingencies, of physics and policy intertwined. At the heart of the grid's complexity is the interplay of control and chaos. The system must respond instantly to a myriad of disturbances, a tree branch brushing a wire, a generator tripping offline, a surge of demand as evening falls. Automation and algorithms help, but the grid remains, in many respects, a living organism, its health dependent on the vigilance and intuition of its human caretakers. And so we return to the visionaries who first glimpsed the possibilities of electrical connection. Nikola Tesla, whose hands conjured blue-white arcs in laboratory darkness, dreamed not only of power for all, but of a world united by invisible waves. His inventions were as much acts of faith as feats of engineering, a belief that the universe's forces could be harnessed, shaped, and shared. Tesla's genius was in seeing the unity beneath apparent diversity. that oscillating currents could knit distant places together, that fields and waves could carry more than mere power, that the grid itself could become a medium for communication and understanding. Yet, in his own time, Tesla was often misunderstood, his ideas dismissed as impractical or delusional. He spoke of wireless transmission of energy, of towers that could broadcast power across oceans, of receivers that could pluck current from the very air. Some of these dreams proved elusive, others, like radio and remote control, became commonplace. But the essence of his vision persists, that electricity is not merely a commodity, but a force that can reshape the possibilities of civilization. Tesla's legacy is everywhere in the modern grid, in the transformers that hum in basements and the high-voltage lines strung across deserts. His alternating current is the lifeblood of our connected world, a river of energy that flows, reverses, and flows again, harnessed but never wholly explained. The full implications of his work continue to unfold as we seek ever more subtle ways to control, store, and deploy the power that flickers at our command. The story of the grid is thus a story of limits and aspirations. For every challenge met, a more efficient conductor, a more robust storage device, new questions arise. How can we build networks that are resilient to storms, to sabotage, to the unpredictable whims of nature? How can we reconcile the need for centralized control with the promise of decentralized generation as solar panels and batteries multiply on rooftops and in garages? How do we ensure that the benefits of electricity reach all, not just the privileged or the fortunate? The grid is a tapestry, yes, but one that is perpetually unfinished, its pattern shifting with every innovation, every crisis, every dream of a brighter tomorrow. It is woven not only from wires and metal, but from the hopes and fears of those who depend upon it. Its threads are both technological and philosophical, binding together questions of equity, sustainability, and the meaning of progress. As we lie in the gentle dark, the hum of electricity all around us, let us listen to the faint, persistent music of the grid, the sigh of transformers, the distant crackle of high-voltage lines, the steady pulse of power moving unseen. Beyond the walls of our rooms, this vast and intricate system carries with it the legacy of Tesla and his peers, the stubbornness of matter, the caprice of weather, and the boundless curiosity of the human mind. And as we drift in the borderland between waking and sleep, we might sense the possibilities still latent in the wires above us, the promise of new materials, the challenge of perfect storage, the hope of a grid that is both more just and more wondrous. The tapestry is not yet complete. Its next pattern awaits the hands and the dreams of those who will come after. And there in that unfinished weave lies the next chapter of the story. Consider for a moment the world as it was just 200 years ago. The night was a velvet tapestry, deep and undisturbed, but for the gentle flicker of whale oil lamps and the whisper of distant storms. The air, on certain evenings, would prickle with a charge before a thunderclap split the silence. A fleeting, wild demonstration of electricity, mysterious and untamed. In those days, the invisible threads that weave through all matter were only beginning to reveal their secrets. The world's greatest minds, armed with simple apparatus and boundless curiosity, were about to set in motion a revolution, to make the unseen not only seen, but harnessed, measured, and transformed. Let us step into the shadowed laboratory of Michael Faraday, a man who, despite his humble beginnings, would become one of the most profound experimental physicists in history. The room is cluttered with coils of copper wire, iron rings, glass tubes, and jars of acid. Candles cast their flickering glow, illuminating the gleam of metal and the intense furrow of concentration on Faraday's face. He was drawn, almost obsessively, to the question: how could one control this elusive force that danced in lightning and made frogs' legs twitch in the now famous experiments of Galvani and Volta? Faraday's approach was not to reason from high abstractions, but to tinker, to probe, to listen to what nature had to say through the language of experiment. It was in 1831, in an unassuming demonstration, that he changed the world forever. He wound 2 coils of wire around opposite sides of an iron ring. When he passed a current through one coil, a brief pulse surged through the second. There was no physical connection, only the iron ring and the silent, invisible field that it channeled. In that instant, Faraday had discovered electromagnetic induction. Electricity could be generated from magnetism and vice versa. With this, the world would no longer be at the mercy of nature's wild sparks. It could conjure electricity at will. To understand how Faraday achieved this, it is crucial to imagine the tools he wielded. His wires, his magnets, his induction rings, these were the first stepping stones. He built the world's earliest electric generator, the dynamo, by rotating a copper disc between the poles of a horseshoe magnet. As the disc spun, invisible lines of magnetic force swept through the metal, setting electrons in motion. A current, steady and controllable, flowed from the machine, and for the first time humankind could generate electricity on demand. The dynamo's hum would one day echo in the vast halls of power stations, but it began as a whisper in Faraday's modest workshop. But Faraday's mind was not content with mere devices. He wanted to see farther, to sense the shape and the behavior of the invisible. He conceived of lines of force, imagining that every magnet and every electrical current was surrounded by a web of influence stretching through space. To many, this was an odd, almost mystical vision, but it became the seed of a profound new way of thinking, that the emptiness between objects is not empty at all, but alive with fields, electric and magnetic, intertwining in elegant, unseen patterns. Decades later, in the quiet of a Scottish study, James Clerk Maxwell picked up Faraday's thread and wove it into a tapestry of mathematics. He did not build coils or turn cranks, but instead conjured equations, silent, powerful tools that could illuminate realms no eye could see. Maxwell's equations, as they came to be known, described how electric and magnetic fields are born, how they grow, and how they move through space. They showed that a changing magnetic field creates an electric field, and, in a breathtaking leap, that a changing electric field creates a magnetic field in turn. Like dancers, the two fields chase each other through the void, giving rise to electromagnetic waves, light itself, and radio, and all the colors and energies that fill the universe. The tools of Maxwell, though intangible, are as real as any wire or magnet. His equations became the master key, unlocking a universe of prediction and design. With them, engineers could build telegraphs and telephones, radios and televisions, radar and lasers. The equations foretold the existence of waves that human senses could not perceive, microwaves, X-rays, gamma rays, and guided experimenters to search for and harness these new forms of invisible energy. Yet, as scientists peered deeper, the tools themselves evolved. The simple magnets and batteries of Faraday's age gave way to ever more refined instruments, vacuum tubes, cathode ray oscilloscopes, and the delicate coils of galvanometers, which could detect the faintest whisper of current. In darkened laboratories, physicists fired electrons down evacuated glass tubes, watching as glowing traces danced across fluorescent screens. These early cathode ray tubes became the eyes with which we glimpsed the electric soul of matter. The galvanometer, in particular, became a trusted companion in the search for understanding. It is a simple device, a coil of wire suspended in a magnetic field, so finely balanced that the tiniest flow of current would twist it, moving a needle across a scale. With this, scientists could measure electricity with exquisite sensitivity, quantifying what was once a ghostly phenomenon. The galvanometer revealed that electricity, so often imagined as a continuous fluid, was in fact made of discrete charges, passing along a conductor in tiny, countable increments. The path of progress then wound through Paris, where the physicist Antoine Becquerel explored the strange behavior of certain minerals. Using a photographic plate and a bit of serendipity, he discovered that uranium salts emitted invisible rays that could expose the plate in total darkness. Electricity, it seemed, was not the only force that could move unseen through space. The tools of investigation, now including photographic plates, Geiger counters, and cloud chambers, grew ever more sophisticated, capable of capturing the tracks of particles and the traces of energies far beyond everyday experience. Beneath these advances lay a new understanding, that electricity was not merely a property of metals or the flow of mysterious currents, but a fundamental aspect of matter itself. J.J. Thomson, at the turn of the 20th century, used cathode rays to probe the atom. With delicate electrometers and ingenious vacuum apparatus, he deduced the existence of the electron, a particle with mass and negative charge, a building block of all atoms and the carrier of electric current. Once again, the tools of the age shaped the questions that could be asked and the answers that could be found. As the 20th century unfurled, the scale of scientific ambition soared. Laboratories grew larger, and their instruments more powerful. Nowhere is this more evident than in the rise of the particle accelerator. In these colossal machines, electricity itself became both the tool and the quarry. By winding vast coils and shaping intricate fields with superconducting magnets, scientists could propel electrons, protons, and heavy ions to near-light speeds. When these particles collided, they shattered into showers of fragments, each leaving its own distinct trace in detectors the size of cathedrals. Consider the Large Hadron Collider, nestled in a circular tunnel beneath the French-Swiss border. Here, modern alchemists wield electric fields of immense strength, guiding beams of protons around a ring 17 miles in circumference. The detectors, enormous, layered instruments bristling with sensors, record the aftermath of each collision with exquisite detail. Every flash, every streak, every trace of energy is captured, digitized, and analyzed. The tools of today's physics are not merely extensions of the hand or the eye. They are vast, collective endeavors, harnessing the invisible with the precision of a symphony. Yet even as the tools have grown in scale and sophistication, the essence of discovery remains rooted in cleverness and imagination. The oscilloscopes of the early 20th century, with their trembling green lines, allowed scientists to watch voltage rise and fall in real time, turning the ephemeral into the visible. The invention of the transistor, a tiny switch made from semiconducting materials, transformed the landscape yet again. With it, engineers could control the flow of electrons with unprecedented delicacy, building circuits that could amplify, compute, and remember. The transistor is, in essence, a valve for the invisible river of charge, and it became the heart of computers, radios, and all the intricate machinery of the digital age. Even the very act of measuring the electrical properties of matter has required all manner of ingenious contrivances. The Wheatstone Bridge, devised in the 19th century, allowed the precise measurement of electrical resistance, comparing unknown values to known standards with a balance as delicate as any jeweler's scale. The Van de Graaff generator, with its spinning belt and crackling hair-raising dome, could accumulate millions of volts, making visible the energy that normally hides in the fabric of air and matter. Through all these inventions, a thread of artistry can be traced, a sense that the tools themselves are not merely means to an end, but windows into the heart of nature. The glassblower shaping delicate tubes for early vacuum experiments, the machinist crafting coils and switches to Faraday's specifications, the mathematician teasing out the implications of Maxwell's equations. Each contributes to the ever-growing arsenal with which we probe the unknown. Yet, for every advance, new mysteries arise. As detectors grow more sensitive, they whisper of particles and forces that have yet to be understood, neutrinos, barely interacting with matter, streaming through the Earth by the trillions, dark matter, whose presence is felt only through its gravitational shadow. The techniques for studying these phenomena now extend far beyond the laboratory, employing satellites that watch for cosmic rays, underground chambers filled with liquid xenon, and networks of sensors listening for the faintest pulse of electrical activity from distant sources. The triumphs of harnessing electricity are written across the landscape of civilization. In the glowing filaments of Edison's first light bulbs, the humming grids of modern cities, the silent transmission of data through fiber optic cables and wireless signals. Yet, amid these achievements, the tools and techniques themselves remain objects of wonder, each a testament to the ingenuity with which humans have reached into the darkness, seeking to grasp the intangible. As the tools evolve, so too does our understanding. The electron microscope, for example, uses beams of electrons, guided by magnetic and electric fields, to reveal structures far smaller than any wavelength of light could resolve. Within its chamber, unseen charges are bent and focused, conjuring images of viruses, molecules, and atoms themselves. The scanning tunneling microscope goes further still, tracing the topography of surfaces atom by atom, using the quantum dance of electrons to feel the very shape of matter. And so the story of electricity is not just one of conquest, but of collaboration between mind and matter, between vision and device. Each tool, each experiment, each leap of theory sharpens our perception, pulling the invisible a little closer to the realm of the seen. Yet the currents of curiosity flow onward, ever deeper. Even now, new generations of scientists and engineers build upon the legacy of Faraday and Maxwell, devising methods to manipulate electricity at the scale of single electrons, to store information in the spin of a particle, to transmit power without wires across open space. The invisible, it turns out, is never truly conquered. It always holds further secrets, waiting for the next clever hand, the next inspired mind, to devise a new tool, a subtler experiment, a sharper lens. Somewhere beyond the hum of cities and the glow of screens, the electric heart of the universe pulses on, awaiting those who would listen more closely, who would shape new instruments and theories to coax fresh meaning from the silent, flowing dark. In the next breath of discovery, new questions begin to form, their answers glimmering just beyond reach, inviting us onward into the unknown. A hush lies over the city, velvet and absolute, just before the dawn. If you step outside in that liminal hour, when the world is neither quite night nor yet truly morning, you might sense the quiet pulse of electricity beneath your feet, coursing through hidden cables, threaded like veins beneath concrete and earth. Street lamps flicker in the distance, their sodium glow painting gentle halos in the mist, while distant buildings keep watch with windows that blink awake, one by one. It is a tableau stitched together by invisible currents, a landscape alive with the silent choreography of electrons. But pause here and turn your gaze inward. Within the soft cocoon of your chest, another current pulses, warm, intimate, ceaseless. Each heartbeat is the echo of a tiny electrical storm, a wave that travels across the delicate architecture of muscle and fiber, coaxing them into motion. Electricity, that ancient and restless force, is not only out there, humming through the latticework of our cities. It is within us, a constant companion, as fundamental to our existence as breath or light. Let us begin with the heart, that perennial symbol of emotion and vitality, and examine it not as poets do, but as physicists and biologists. At the root of every heartbeat, at the threshold between stillness and contraction, is a minute but vital spark. Specialized cells, nested deep within the right atrium, form the sinoatrial node, a cluster so small you might overlook it, yet it is the maestro of your body's rhythm. The cells here possess a remarkable property. They can generate electrical impulses spontaneously, a phenomenon known as automaticity, The source of their spark lies in the orchestrated movement of ions, sodium, potassium, calcium, slipping across cellular membranes through carefully regulated channels. With every pulse, these ions shift position, creating an electrical gradient, a wave of charge that ripples outward. This pulse races along specialized pathways, fibers and bundles that guide it, like electrical wiring. It reaches the atrioventricular node, then cascades down through the bundle of His and the Purkinje fibers, urging the ventricles to contract in perfect synchrony. Each beat is the harmonious result of millions of microscopic charges racing in concert, a symphony of movement and rest, of charge and discharge. You might picture the heart as a tiny, self-contained power plant. But it is more than that. It is a relay, a node in the greater web of your body's electrical system. Beyond the heart, networks of nerves snake their way through flesh and bone, relaying messages in the language of voltage. A thought is born as a flicker in the cortex, a cascade of ions across synapses. When you lift your hand, when you catch a scent on the breeze, when you recall a childhood memory, all of these are, at their core, electrical events, orchestrated by the flux of charged particles. The neuron, that slender and enigmatic cell, is the true conduit of these signals. Its membrane is a living barrier, a phospholipid sea studded with protein gates, each one sensitive to the dance of ions. In the resting state, a neuron holds a delicate tension, an imbalance of charge across its membrane, a potential waiting to be unleashed. When stimulated, the gates swing open, sodium rushes in, and the membrane depolarizes, propagating an action potential, a wave of voltage that zips down the axon at astonishing speed. When the signal reaches the synapse, it triggers the release of neurotransmitters, bridging the gap to the next cell, and the cycle continues. In this way, electricity is the language of the body, swift, efficient, endlessly adaptable. It is how we sense the world, how we move, how we think. It is the invisible ink of consciousness itself. Step back a moment and consider the paradox. We, creatures of flesh and thought, are animated by the same force that crackles in a thunderstorm, that arcs between clouds and earth with a violence that can split trees and set the sky alight. Yet within us, electricity is tamed, domesticated, woven into the very fabric of life. Our nervous systems are, in a sense, networks of living wires. The ancient Greeks, who first glimpsed the mysterious power of amber rubbed with fur, could never have imagined how deeply entwined their discovery would be with the essence of living things. But our relationship with electricity does not end at the border of skin. Humanity's genius lies in its capacity to reach beyond the body, to reshape the world and harness the powers of nature. Over centuries, we have learned to coax electricity from the slumbering earth, to summon it from wind and water, to release it from the bonds of chemical fuel. The history of civilization is, in many ways, the history of our evolving partnership with this elusive force. Close your eyes and picture the city as night recedes and day begins. Below the surface, cables as thick as a wrist carry thousands of volts, branching into ever finer filaments until they reach the lamp above your bed, the kettle in your kitchen, the phone in your hand. Each switch you flip, each charger you plug in, is a quiet invocation, a request for a sliver of the grid's vast and humming bounty. But what is the grid, this modern marvel that delivers the lightning of the gods to our fingertips? At its heart, it is a vast, interconnected system, a mesh of wires, substations, transformers, and power plants stretching across continents. Electricity is generated by spinning turbines in dams, by burning coal or gas, by capturing sunlight or the restless wind. It is then shaped and stepped up to high voltages, transmitted across great distances, stepped down again, and finally parceled out to homes and businesses in precise, measured doses. It is a system of staggering complexity, yet it remains perpetually on the edge of balance. The grid must match supply and demand almost instantaneously, for electricity is not easily stored in large amounts. Too much, and the system overloads. Too little, and the lights flicker and die. Behind every moment of illumination, every whirring appliance, there are teams of engineers, algorithms, and machines, all laboring to keep this delicate equilibrium. Our dependence on electricity is profound and nearly total. It illuminates our nights, powers our industries, and connects us across continents. It enables the marvels of modern medicine, MRI machines that peer inside the body with magnetic precision, ventilators that breathe for the frail, pacemakers that whisper life back into faltering hearts. It is the currency of the digital age, the blood of the internet, the silent partner in every transaction, every message, every fleeting thought shared across the globe. Yet this dependence brings with it a host of questions, practical, philosophical, and ethical. For every watt that flows into our homes, energy must be drawn from somewhere, transformed from one form to another, with consequences that ripple outward. The burning of fossil fuels, the damming of rivers, the harvesting of wind and sun, all these have shaped our world, for better and for worse. We find ourselves at a crossroads, poised between abundance and fragility. The grid is a marvel, but it is also vulnerable. Storms can rend its lines, solar flares can disrupt its pulse, cyber attacks can threaten its integrity, and above all, our appetite for energy grows ever greater, straining the limits of what is sustainable. There is a deeper question too. What does it mean, in the grand scheme, to be so reliant on something so intangible? To entrust the rhythms of our days and the beating of our collective heart to the flow of electrons? Are we, in some sense, less free, more beholden to the systems that sustain us? Or have we, through ingenuity and curiosity, simply woven ourselves more tightly into the fabric of the universe? Consider the ethical challenges of energy production. Every method of generating electricity has its costs and trade-offs. The coal-fired plant belches carbon and mercury, warming the atmosphere and fouling the air, yet it is reliable and potent. The dam submerges valleys, alters ecosystems, uproots communities, yet it provides clean, renewable power for generations. The nuclear reactor offers vast energy with minimal emissions, but its waste is long-lived and its failures catastrophic. Solar and wind are clean, decentralized, and increasingly affordable, but they are fickle, bound to the whims of weather and the turning of the earth. Our choices matter, not only for ourselves, but for the generations yet to come. To flick a switch is to draw upon the labor of countless hands, the ingenuity of engineers, the bounty of nature, and the sacrifices of those whose lives are shaped by mines and rivers, fields and reactors. It is to participate in a vast and ongoing story, one whose consequences are written across landscapes, atmospheres, and lives. Yet there is a quiet hope in this interdependence. New technologies are emerging, batteries that store the sun's warmth through the night, grids that adapt and learn, devices that sip rather than gulp their share of power. Cities are reimagining themselves, adding solar panels to rooftops, weaving green corridors through concrete jungles, striving to balance comfort and sustainability. The conversation has shifted, slowly but inexorably, from one of extraction to one of stewardship. And beneath all these practicalities, there is the philosophical wonder that a force as simple and as profound as the movement of electrons can be the foundation of so much, of life, of thought, of civilization itself. We are, in a very real sense, charged with life. Our hearts beat to an ancient rhythm, guided by electrical pulses that echo the storms of the cosmos. Our cities glow with the harnessed power of rivers, winds, and stars. Perhaps then the flick of a switch is more than a convenience. It is a moment of connection, a thread that links us to the earth and sky, to the engineers and dreamers, to the past and the possible future. It is a humble act, yet it is also a leap of faith that the grid will hold, that the current will flow, that the invisible world of electrons will continue its silent, ceaseless work. And so, as you settle into the hush of your room, as the soft glow of a lamp steadies your thoughts, and the background hum of devices lulls you towards sleep, you might find yourself pondering the mysteries that lie beneath the surface. What unseen currents shape your world? What quiet miracles unfold with every heartbeat, every thought, every light that flickers to life in the darkness? Outside, the city stirs. Somewhere a distant turbine turns, its blades slicing the wind. A panel drinks in the first rays of morning. A river tumbles through concrete channels, spinning copper coils deep within a dam. All these movements, all these harnessed energies, converge in the silent, dependable delivery of a spark. And within your chest, the pulse of your own private current keeps its time steady and sure, a reminder that the boundary between the natural and the technological, the living and the made, is more porous than we might imagine. We are, all of us, bound together by the restless dance of charge, a dance as old as the stars, as intimate as a heartbeat. The story of electricity is, in the end, the story of connection between cells, between cities, between the earth and the sky, between the past and all that is yet to come. As you drift towards sleep, let the thought settle gently, that every moment, every flicker, every quiet surge of current is a part of something vast, mysterious, and profoundly alive. In the soft darkness, as currents both internal and external flow, the world continues its silent weaving, a tapestry of light and life, charged with possibility, humming with dreams not yet dreamt. As our journey through the shimmering currents of electricity gently drifts to a close, may the quiet dance of electrons and the vast hum of power grids linger softly in your mind like a comet tail fading into the hush of space. Rest now in this peaceful glow, and when you're ready, return with me for more Dreamtime tales that light up the wonder of our universe.